Thank you.
Okay. Hello, welcome to the webinar Finite Element Modeling of Existing Masonry Towers, the Asinelli Tower. This study makes part of the numerical simulations of Masonry Towers line of research from the Politecnico di Torino. This research is the work of your speaker, Natalia Lozano, and has been supervised by Professor Stefano Invernizzi. This presentation is divided in 4 fundamental parts. In the first part, I will talk about the case study and its general characteristics. In the second part, I will talk about the construction of the 3-dimensional finite element models in FX plus for Diana and the mechanical properties adopted. The third part consists on the different analysis using the Diana mesh editor, the comparisons between models, and recent experimental tests. Finally, I will quickly explain the conclusions and possible future research works. The case study is found in the Bologna city center. The Asinelli Tower at the left of the picture is the highest tower and oldest masonry structure in the city from the year 1109. The Asinelli Tower is also the highest leaning tower in Italy and a viewpoint from which it is possible to peer into every part of Bologna. Together with its adjoining tower, the Garisenda Tower, it stands as the symbol of the city. In 2009, a high-resolution survey was performed thanks to an innovative terrestrial laser scanning system. With this technique, it has been possible to obtain a 3-dimensional georeference model through which the real overhanging, the tilt, and detailed geometry have been determined. This information was translated in detailed plans that we have used for the construction of the finite element models. The Asinelli Tower is a 98-meter high tower with a structure made of 4 main segments depending on the characteristics of the cross-section and differences in the material of the masonry. The first part is made of a brick and rubble masonry structure made of 2 brick faced walls and a rubble core filled with mortar, bricks, and stones. The second is a brick and rubble masonry wall segment of shorter thickness. The third one is a solid brick masonry wall cross-section of a thickness of 1 meter, holding the fourth part, which is the masonry belfry. The foundation is made of 2 different parts, a conglomerate foundation base with wooden piles, and a selenite block and rubble base surrounded by a masonry portico. The tower has been reinforced over the last centuries through a series of steel cables and chains, which I will explain later in more detail. The 3-dimensional models developed have increasing complexity, as you can see. The first model is composed exclusively of a hollow trunk and a quadrangular prism as the foundation. A second, slightly more complex model represents the infill of the brick and rubble masonry structure. The last model has a more intricate shape, as close as the real tower as possible. It contains the rubble infill, as well as detailed elements like window openings, the belfry, the reinforcement, and the portico. The foundation, as in reality, is divided in 2 different parts, counting also for soil structure interaction. These 3 models were chosen to assess the difference between the modeling procedure, the computational efficiency, and the accuracy of the results. For the finite element modeling, the FX Plus for Diana program was used, and for the structural analysis, the software Diana mesh editor was used. Regarding the finite element modeling, we identified 3 main procedures to be used depending on the information available and preferences of the modeler. The first approach is to import to FX Plus the section lines previously constructed on a CAD program. This procedure can be adopted when the model plans are available in advance, for example, for our complex model. A second alternative is to model the section lines directly in FX Plus. This strategy requires a better understanding of the software. These two options require the use of the different tools and Boolean operations that FX Plus provides to generate the solids, for instance, the loft command. The third choice is to import the solid elements from a CAD program to FX Plus. This procedure is effective when a 3D model of the structure has already been built. A very important step should be made before the discretization of the solids. The embed command should be used between solids inside other solids, but also between adjacent solids to guarantee that common contours between elements are imprinted on each other and nodes from the different elements match. This step will avoid the generation of errors and incorrect results from the calculation. I will explain this more deeply in the modeling example I will be showing you. So, to illustrate one of the procedures, I will show you the complete process we took to build the complex one model. This model was constructed importing the lines to FX Plus, so we took the first procedure mentioned before. These will be the steps I will be showing you to finally arrive to this solid model. I will be showing the commands to use in the upper part of the slide and the commands and options for future reference, since you will have access to this presentation in the future. So first, we import the lines by clicking File, Import, DXF3D wireframe, and we select the file and we click Open. You will see the polylines are imported in blue and the lines in black. Then we start creating the solids. So here I've shown just the polylines of the tower's trunk. So we select solid, loft, select the profiles in the correct order. So 1, 2, 3, 4 or backwards. 1, 2, 3, 4. We check solid and straight to generate the volume in a correct way, and we click Apply. This procedure will end up in this solid right here. I have changed the color and transparency of the solid so you can see the final result. If we continue with the same methodology, we will obtain these solids right here. So I have also generated the solids of the void. So how do we generate these voids? We can use the command embed to extract a volume from another. So we select first solid option, we go to embed, we select the master object, which will be the outer solid, the Masonry, and then we select the tool object, which will be the void. We check delete original shapes because this option deletes the original two volumes and leaves just the generated volumes. And then we click Apply. So we generate these two solids, one extracted from the other. If we don't need it, we can go ahead and delete the inner volume. If we continue to do this procedure, we will obtain these volumes right here. If we make a close-up of the solids generated when I select the hollow trunk, we can see that these two lines right here, this and this one, are not imprinted on the first solid, on this solid. If we don't print them, when we generate the mesh, these lines will not be generated on the solid, and this fact can lead to calculation errors. So what we should do is to use the command embed again to print the lines on the adjacent solids. As I said, it is incumbent to do so, since the meshing will be made correctly. So what we do is to select the solid option, we go to embed, we select the master object, which is this solid to print on, and then we select the tool object, which will be this one with lines to print on this one. we uncheck the delete original shapes because since the solids are not intersecting, just touching by a face, the tool will be deleted. Oh, sorry. Okay. The tools will be deleted. So what we do is uncheck master object. We selected this the hollow trunk. Then we select the tool object and then we click apply. So this procedure will generate the two lines you can see right here on the solid. However, the original solids will be hidden, so we need to show them in order to delete the original Masonry trunk. We make right-click on the geometry option in the pre-works window and we click show all. Or we click the individual solids on the list and show them, whatever works better for you. So then we delete the original trunk, meaning the one that doesn't have the lines imprinted. Of course, this procedure can be confusing, so it depends on what you prefer. So finally, we have the solids correctly modeled, including the adjacent lines right here on the hollow trunk. The next step is to generate the voids from the openings, following the same procedure I explained before, generating the solid on the void using the loft command or any other Boolean operation, and then extracting it from the master solid with the embed command. The same goes for the rubble infill, which I will be extracting from the Masonry trunk also. To do this, again, we use the command embed to open the voids, but also to print out the contours. These are the final solids model. Remember to use the embed between solids to print out the contours. For example, the portico and Masonry trunk have lines here in common. So you should repeat the process again. This is the final result without transparency. So, the finite element method accounts for the discretization of the domain, or total volume in this case, in a finite number of elements with nodes in its boundary, to substitute the infinite number of degrees of freedom of the domain with a finite degrees of freedom system. Subsequently, it is necessary to choose an interpolation function between the element nodes to guarantee the compatibility in the adjacent boundaries between elements. On the left, we can see the number of elements and nodes for each model, a quantity that increases proportionally with the complexity of the model. This affects, obviously, the computational power and space required. For the discretization of the solids, we chose the CTE30 element, which is a 10-node, 3-side isoparametric solid tetrahedron element. The mid-side nodes on each side, here, 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 and here, affect the interpolation because it's a quadratic equation. For the discretization of the reinforcement bars, the bar in solid type of element is used. We differentiate two types of reinforcements, one being constructed in the year 1706 as rectangular cross-section metallic strips, and the other constructed in the year 1913 as circular cross-section metallic bars. Lastly, we used a CT36I element according to the Diana manual, which works as a 6+6 nodes interface surface on a 3-dimensional configuration. This is used to model the solid structures interaction as a Winkler model, which means representing the foundation subgrid as a finite number of springs under a structural rigid base. In this case, the foundation base and Masonry portico, as you can see here. This element is concordant with the CTE30 solid element chosen, since it is a quadratic interpolation-based element with 6-point integration scheme, meaning it has a mid-side node on each edge. match. If you are interested in knowing more about the types of discretization elements, you can consult the Diana's Element Library manual. So this is how the final models look discretized. The isotropic material properties used can be seen also in this slide. For the first model, the properties are obtained from a model identification study made from a similar model of this tower. For the second type of model, the properties used are extracted from experimental tests done on the actual tower and model identification theoretical procedures on higher complexity models. For the third model, we use the properties from the previously mentioned research study and also some common properties for which the values haven't been yet published. So meaning we assume some values or calculated them through model identification procedures. So how do we generate the discretization? Again, I'll show you the example of our complex one model. So first we need to define the materials and properties. We proceed to click the analysis option and then material. To generate a new material, we click create, and in the isotropic tab, we define the first four materials by writing the corresponding properties, this right here, these four. And then we click apply. Lastly, in the interface tab, we write the two values of stiffness requested for the type of interface material, and then we click OK. A very similar procedure is done for the properties definition. So we select again the analysis option and we click property and then create. Selecting the 3D option, in the list we generate the first properties. Lastly, with the interface option and interface surface tab, we create the interface property. Then we can proceed to discretize the solids. So to improve the quality of the mesh, we chose to begin with the foundation solids, then the infill, so the inner solid, and lastly the outer solid of masonry trunk. To do this, we click Auto Map Mesh and select Auto Mesh Solid, since our 3D mesh element is a tetrahedron. We select the solids to be meshed right here, and we choose element size 1.15 meters for our case, or you can also choose division. Then we choose the correct property, write the name and click apply. Notice that this solid right here has a square imprinted on the upper face from the foundation base above it. Here we see the element already discretized. Notice that thanks to printing the square, the mesh took into account this shape on the foundation face. That's why I told you that using the embed to print out the contours is very important. So this is the final result of the mesh. We can see the zoom over here. You can see the tetrahedron elements. Now to generate the interface, we need to show only the mesh sets touching the interface. So in this case, the conglomerate and the masonry. We do this by selecting each of these sets and right-clicking the Show Only option. We can change to From View right here. First, we need to generate a mesh under the existing mesh sets by selecting the Protrude Mesh option here and then Extrude. In the Element Face to 3D tab, we select the faces, meaning this face is right here touching the soil, here and here. Then we can select 2-point vector as the extrusion direction, writing -1 in the Z direction on the second point, since the extrusion needs to be generated in this sense, right here, in the negative Z direction. We write the length size and number of deletions, in this case 1. And finally select the property, which can be any, since we will change it in the next step to interface, and mesh set name. We click OK. The mesh is generated, so now we should convert it into an interface element. We select mesh and create interface element right here. The type is plain. The method we can choose is convert element. First we select the mesh elements, and after we select the base nodes, meaning the nodes between the mesh elements touching the interface and the mesh elements previously generated. So these nodes right here and these nodes right here. Here is where we select the interface property and finally click OK. This is the result of the interface. We can see the mesh set created over here in the list. We can choose either to move this surface back, this and this back to the initial position, or leave like this generated to apply the boundary conditions later. Either way, the program will read the element as a surface interface and results will not change at all, so you decide. So if you remember, I mentioned that the 3D solid element used for the mesh was a 10-node element with mid-side nodes on the edges. To convert this element, we go to Mesh here and change element parameter. We select all the mesh sets, selecting to change order option, then quadratic right here, and check the mid-node to geometry option. When we click OK, if we show the nodes of the elements, you will see that the mid-side nodes generated in both the 3D elements and the 2D elements right here. The last type of element to be defined is the bar in solid, so the reinforcements. First, we define the reinforcement material with the procedure mentioned before: analysis material, create isotropic material. Then we define two different types of reinforcement bars in the properties section: the 18th century ones and the ones from the year 1913 that have different cross-sectional areas. So what changes is this right here. We need to define also the bar sections. So we select create reinforcement and go to the reinforcement bar section 1D right here. We then define two different bar sections, as you can see, selecting curved shape for each type of reinforcement. So now, to discretize the reinforcement, we select the Auto Map Mesh option and click Auto Mesh Edge. We select the first type of reinforcement, highlighted in pink right here. Choose the seeding method, interval length, and write 1, since the internal connections with the solid elements will be done automatically by the program. We choose first the bar section property right here, and later the reinforcement bar property. When we define the name, we click apply. It looks like this, so we repeat the same process for the second type of reinforcements, and finally end up with these colorful lines that represent the bar instance already meshed. A new list is displayed in the mesh list called reinforcements, as you can see here. Finally, before proceeding to the analysis, we define the boundary constraints. So the first step is to define the boundary condition set. So we select the analysis option and BC set. We should write a name and a description right here, and we generate the supports for the base of the structure and cables or reinforcements to limit the rotation of the reinforcement on their ends. Later, we select the analysis option and choose the constraint command right here. You should choose the BC set previously defined, type of object node, and select the base nodes or ends on the reinforcements, depending on what you're doing, and choose the respective degrees of freedom to be limited by right here. Notice that we selected just these nodes, this right here and this right here, in the lower surface of the interface. If you select the nodes in both surfaces, it's like the interface doesn't exist. So because you will be restricting the top part, you just need to restrict the lower part. So these are the boundary constraints assigned. We can see in this close-up the different degrees of freedom in each type of element. We can also see that boundary conditions are applied to the bottom surface of the interface elements. Subsequently, the three models are subjected to a series of analyses to obtain some parameters that will be compared. So, for a group A of analysis, the three models with isotropic materials are used for a linear static analysis and a model analysis to obtain the roof displacements, the vertical stresses, natural frequencies of vibration, and the model shapes. For a group B, the three models with isotropic and nonlinear properties of the material are subjected to a model analysis and a nonlinear static analysis to obtain the capacity curve and real cracking pattern. Finally, for a group C, an anisotropic model of the brick and rubble masonry material is proposed for the complex one model right here to consider the damage present in the masonry due to vertical cracks, to compare the natural frequencies between different levels of damage. For the group A of analysis, we need to determine first the body force. Going to analysis option and body force right here, this button. Defining the load set as the gravity force with -10 in the global direction 3, we consider the self-weight. We can see that the self-weight load set generated right here on the load list on the pre-works window. To start defining the analysis commands, we go to Analysis tool in the top bar and click Edit Model with Diana Mesh Editor right here. This option will open the mesh editor software Diana comes with. So to define the analysis commands, we click Analysis and Add Analysis, or we click this button. And so this analysis one is created. Then we select Analysis and Add Analysis command, or this button right here. We choose a structural linear static, which displays this list. Then we select Analysis. After we select this analysis, on the Properties window, we can see that you can define the methods of the system of equations, are the device of the results, in this case the Midas fx plus for Diana. We can repeat the same process to define the model analysis. So this is called structural eigenvalue. In the Properties window, we define free vibration eigenvalue type, the number of eigenfrequencies, and in this case 12, and the device for the output, which is again Midas fx plus for Diana. You can now save these analysis commands for future needs, because of course you know the structural analysis is an iterative process and you are going to need to repeat this procedure a lot of times. So you do this going to Analysis right here and save analysis commands. This procedure will save a .dcf file that you can open again by clicking Analysis and Load Analysis commands. Finally, you click the Run button, and once the analysis is complete, you come back to FX Plus and right-click on the Results window, select Import Results, and add first the .dbp file, I think it is, and the .dmb file that contains the reinforcement results. So then you click Import. For the first group of results, specifically from the linear analysis, in the three models, we obtained the roof displacements and vertical stresses in the masonry. On one side, the roof displacements are very similar, going from 9 to 12 centimeters. This result agrees well with a previous study about the monitoring with acoustic emissions and structural modeling of the Asinelli Tower made by the Politecnico di Torino in 2013, in which they obtained an 8 centimeter roof displacement in a very similar model compared to our simpler model. Regarding the vertical stresses, we obtained this figure in which the tensile stresses are those positive and lower values, and the compression stresses are those negative and higher values, as expected in a masonry model. The most stressed part is concentrated in a very limited area at the base of the tower, below the direction of the greater inclination, meaning southwest, and a situation showed also, though the percentage of elements under this stress, which is a little lower than 0.1%, as you can see here. In this exact position, the acoustic emissions monitoring was developed, meaning the models represent a real distribution of stresses. So later, the model analysis results are condensed in these 4 squares right here. In this tree, I'm showing the first 3 couple of bending modes, and in this one, I'm showing the first torsional mode. The fundamental period arrives to 2.8, 3.2, and 3.3 seconds, respectively, for the 3 models of our study, showing a very flexible behavior expected for a tower of this kind. The model shapes and the mass participation percentage are very similar to previous studies and between the models, but slightly different for the more complex model. The natural frequencies obtained are compared with the natural frequencies from theoretical models of the tower developed in the last 2 decades and experimental measurements of the frequencies. The first one, the first model, is a beam model with a foundation made from a rigid block with springs. The second one is a shell model with flexible base. The third one is the most accurate of 6 models developed recently. It is a shell model with flexible base, solid structure interaction, P-delta effects, and orthotropic masonry. The last model, as mentioned before, developed by the Politecnico di Torino, is a 3-dimensional model with fixed base. The experimental measurements of the real natural frequencies were obtained in 2012 during 3 months by the Italian National Institute of Geophysics and Volcanology. From the monitoring with 4 accelerometers positioned in different heights inside the tower. Here I'm showing the Fourier graph, where the most amplified frequencies were identified and highlighted in our graph as intervals. This comparison graph shows the frequencies on the first 3 bending modes and the torsional mode right here against the frequency values when available. From this, we can say that in general all models reach the real structure response. The first and second models achieve just the first frequencies. The third model response is close to all frequency intervals and is similar to our complex one model right here. The fourth model has a very similar response to our two simple models. We can identify an approximation to the real frequencies with an increase of three-dimensional model complexity. In fact, the complex one model is the one that has the closest to reality structural response. Finally, we have learned from the third research that in the intention of getting close to the real torsional frequency, the researchers have sacrificed also the bending frequencies, lowering them. In all models, it is noticeable that the torsional frequency is the hardest one to reach, probably to a wrong approach. So, how do we lower significantly this torsional frequency right here without lowering the bending frequencies? This is where we reasoned about an anisotropic model of the Masonry material. So jumping to the C group of analysis mentioned before, it is safe to say that there are many and very thorough Masonry anisotropic models in the scientific literature. However, these models are typically based on the fact that the anisotropy is caused by the heterogeneous disposition of bricks and mortar and have the purpose of transforming the mesostructure in a continuous anisotropic model through homogenization processes. The model we propose here is slightly different since we are convinced that the fundamental cause of anisotropy is the presence of damage induced by cracking, and that this is far more important than that of the masonry weaving. In this way, we consider anisotropy due to damage, which we have detected as predominantly vertical cracks, meaning the mechanical properties to be affected will be the ones in the horizontal direction. So for the implementation of the material anisotropy, we have used a smeared crack model in which both the elastic and cracking strains are considered because it is evident that the strain will be larger in the presence of this damage. This model involves the implementation of a second stiffness, which is later translated into traditional parameters right here, that multiply the elastic characteristics. For further explanation, you can check the Diana's theory manual. Instead of using these parameters, we have used a damage parameter that multiplies and decreases gradually the mechanical property values in the horizontal direction. This means the damage parameter equal to 1 represents the isotropic material, and the smaller values of damage parameter give the material an anisotropic characteristic, or more in detail, a transversely isotropic characteristic. To do this, we also made a series of verifications to guarantee that the stiffness matrix was also always positive. Okay, so here you can see the properties of this, the materials with the damage parameters. To define these materials in fx+, we simply created two different materials for each damage parameter. For the damage parameter equal to 1, which is the isotropic condition, we have already created the material property. So we need to create a total of 8 new material properties. We use this table to fill in the property values. So you go to Analysis, Material, Create, and select the tab 3D orthotropic. I've shown here the corresponding properties for the anisotropic brick with damage parameter of 0.9. You should continue the same process to create the other 7 materials. To assign the material to the property, it is not necessary to create a new property. You can simply modify the material assigned to the masonry and infill properties. by going to Analysis, Properties, select the material, click Modify, and change the material, for example, to the 0.9 damage parameter material we just created. You do the same with the infill, and you have already the model with the 0.9 damage parameter materials. To open the mesh editor, you go to Analysis and Edit with the mesh editor. Once the mesh editor is open, you select Analysis and add Analysis. You can change the name for example, Asinelli Tower, the equals to 0.9. It is important to distinguish the different analyses, since we are interested in having different result files, one for each damage parameter. So to not repeat the procedure, we can load the previously saved analysis commands. So we go to Analysis and Load Analysis Command. We can delete the structural ingredient static right here in this button, since we are interested just in the model analysis. We check the model analysis properties, and if everything is okay, we click Run. And once the analysis is done, you already know how to open the results files in the FX+, and then you can continue doing that. So, applying this parameter gradually by assigning the different material to the Masonry and infill properties, we had different result files, and we plotted this graph showing the damage parameter against the natural frequency values for the first couple of modes. We can see again the intervals of experimental measurements of natural frequencies and the tendency line for each type of frequency, either from a bending, here, here, and here, or torsional mode, right here. We can see that we reach quickly, to show you, the torsional frequency, because the tendency line is low, this one right here, is much more significant than those for the bending frequencies, this one, and this one. In this way, we have found that a damage parameter equal to 0.8 is the one that best achieves the real response of the tower, because all frequency agree with experimental measurements intervals, as you can see here also. This also means that the present damage due to cracking in the tower represents a % of decrease in the mechanical properties of the masonry brick and rubble material in the horizontal direction. So, I will just erase this. Okay. As we know, sometimes the linear analysis cannot be representative of the structure's real behavior, and therefore it is necessary to perform a nonlinear analysis to obtain the ultimate limit state response. The European codes consider the implementation of nonlinear analysis for structures in which the residual strength and stiffness are influenced by the present damage, in this case the historical constructions. As part of this research, we performed a model pushover, which is a nonlinear static analysis that applies an acceleration proportional to the first model shape. For more information, you can check the Diana analysis procedures manual. With this analysis, it was possible to determine the capacity curve for each model, meaning the roof displacement versus the base shear, through the N2 method, or equivalent displacement method, which idealizes the structure as a single degree of freedom system to obtain a reduction factor. To explain all the process to define the pushover load is a little bit long and we don't have enough time, but I will explain the main idea very quickly. If you're interested in step-by-step process, you can always contact the Diana support. Well, after you define the isotropic materials in FX+, you open the mesh editor and go to the model tab. And in the material section, you make right-click on each material. You select Edit Material, and from here, you select the class of material and the material model. There are a lot of possibilities, as you may know. So after you click OK, you continue determining the characteristics of each material model you chose here. After defining all the materials, you should export the model in point dot, saving it from File and Export Model. You can then open this file on any text editor and copy the exact text under the loads line, this right here. This number is the name of the model elements that the program will take into account. If you are not sure, you can write a bigger round number. Anyway, the mesh editor will take the exact number of elements. Now we import the model in the mesh editor by clicking File, Import Model, and selecting the point.dat file that you just saved. You can see in the messages box that the program automatically removed the non-existing elements. You now create a new analysis that I called here pushover and add two new analysis commands. One is the model analysis that I previously explained, and the nonlinear static analysis called structural nonlinear, in which you will define one execute block that will represent the dead load, and another execute block representing the pushover load that will start right after the dead load application. So taking also into account the first model shape from the free vibration eigenvalue analysis. There are some options here you should define, like the nonlinear effects, the load steps, the equilibrium iteration, and also the output, where you will define the results you want from the analysis in the user selection section. So you have the option again to save the analysis commands to load them for future analysis, because you will of course need it again. And after that you save the file and click Run. And then you can come back to FX Plus and open the results as we saw before. So these are the three capacity curves obtained from the pushover analysis, one for each model. So first we look at the simple one curve, which is the one with higher base shear and lower yield displacement. So for Masonry towers, the Italian codes contemplate a reduction factor, or called behavior factor, for towers with presence of abrupt changes in stiffness along the height. This factor is equal to 2.8. For the simple one model, we calculated a very close but lower reduction factor of 2.3. The cracking model shows concentrated damage in the tensile area and the lower part where the stiffness changes abruptly. In the second model, the cracking is still developed in this area right here. The regular capacity curve is caused by fragile cracks that change suddenly the course of the curve. We can identify a lower capacity by the curve and by the reduction factor 1.9, still lower than the one from the code. At last, for the complex one model, we can see a more detailed cracking model in which we can identify a much more widespread damage due to the presence of openings, wall section differentiation, changes in stiffness due to the portico and the belfry, and so on. These details trigger and propagate cracks, lowering the capacity, but generating a more regular curve because of the more accurate ductility modeling. The reduction factor is 1.7, 40% lower than the required by the code. So finally, from what we achieved in the modeling and analysis procedures, we can make the following conclusions. From the linear static analysis, we obtained values of roof displacements and vertical stresses similar to those of previous models. These show greater flexibility while increasing the complexity of the model. From the model analysis, we can conclude that the more complex the model is, the better the actual response of the tower was achieved. However, the Winkler model adopted for the solid structure interaction turns out to be too flexible for this three-dimensional finite element model, forcing the stiffness values to be higher than expected. So in this way, further research in the solid structure interaction for this type of structures is strongly advised. Also, the introduction of a damage parameter that accounts for vertical cracking damage in the masonry becomes an efficient and easy to apply model, since the anisotropic model proposed showed the importance of considering the damage in structural analysis. Future and more detailed research is encouraged on this matter. According to this model, the Asinelli tower presents a 20% of decrease in the mechanical properties in horizontal direction due to the presence damage due to cracking. Lastly, the nonlinear analysis implementation has revealed that a more detailed model represents a lower capacity than the simpler models in the code. Especially looking at the cracking configuration, the complex one model develops a much more real local pattern. For this topic, further research is encouraged as well. If you need more information about the several topics I spoke, I left the specific references on each slide in the bottom box, so you can check these references slide. Besides, if you need to make questions, you can make them right now, or you can always contact me via email. Thank you for your attention and interest on this research.